In the previous lectures, we have studied the 2D transformation, how 2D transformation metrics are represented, okay, different types of geometric transformation in 2D. So now we'll go for 3D transformation. Okay, so we'll go for 3D transformation. So geometric transformation in 3D space. A three-dimensional object has a three-dimensional geometry, so therefore it requires a three-dimensional coordinate transformation. So a right-handed coordinate system is used to carry out a 3D transformation. So the scaling and translation transformations are essentially the same as 2D transformation. However, the points matrix will have a non-zero third column. So additionally, the transformation matrix contains some non-zero value at third row and third column. So 3D transformation extend from 2D transformation by including a consideration for the z coordinates also. So the translation and scaling are similar to 2D dimension, including the 3D Cartesian coordinates. So the rotation methods is less straightforward. So the representation of the 2D transformation is usually by 3D 3 elements matrix, 3 by 3 element matrix. But in this 3D transformation, the matrix is 4 by 4. So we are additionally adding one third coordinate in z coordinate, and we are representing the matrix by 4 into 4. So geometry transformation 3D space can be 3D translation, 3D scaling, 3D rotation. So in 3D space, the geometry transformation can be given by this 4 by 4 element. So in the translation, we will get the translation factor tx, ty, tz, and in the rotation also there are 4 factors. Then if you go for a scaling, there is sx, sy, sz, they are the scaling factors, and the fourth we are putting identity matrix for 1. So relative to coordinate origin, just include the parameter for z coordinate, including the transformation matrix. So xj, the xj, x dash, by dash, z dash 1, they are the coordinates of the initial scaling method. This final scaling or after the scaling transformation. So if you multiply the this scaling matrix by the original point, then you will get the final coordinates. Okay. So for if you are getting the scaling with relative to the fixed point except by ZF. So we are performing a translator scaling translation complete transformation. So if you will go for three-dimensional rotation definition, so we are assuming that looking in the negative direction along the x-axis. So positive angle rotation produces counterclockwise rotation about a coordinate axis. In the diagram, you can see if you are seeing from z-axis how counterclockwise is the given positive angle. If you see from the x-axis how the positive angle is taken in counterclockwise direction. If you see from y direction how the counterclockwise uh, rotation are given positive angle. So geometry transfer in rotation, you can see three-dimensional coordinate axis rotation RZ. If you are rotating the object according to along the z axis, then what is the equations for the z axis? X dash equal to x cos theta minus y sin theta, y dash equal to x sin theta plus y cos theta, z equal to z. So if you are rotating the object on the z axis, then this rotation matrix will be cos theta minus sin theta 0 0, sin theta cos theta 0 0, then z dash equal to 0 0 1 0, then 0 0 0 1, and if you multiply this matrix by this initial coordinate of the object x y z1, then you will get the final coordinate of the object. So transformation equations for rotation about the other two coordinates axis can be obtained by cyclic permutation. So x-axis rotation equations: y dash equal to y cos theta minus z sin theta, z dash equal to y sin theta plus z cos theta, x dash equal to x. So Rx rotation about the x-axis, we can say that these final coordinate equations. So if you will rotate the object around the y-axis rotation, then equations will become like this. So final coordinate point is z is equal to z cos theta minus x sin theta. X is equal to x z sin theta plus x cos theta. But is equal to y. So this is a rotation matrix in the 3D transformation if you're rotating over the y-axis. So general three-dimensional rotations consist of three steps. First, you translate the object so that the rotation axis coincide with the parallel coordinate axis. Then perform the specified rotation about the axis. Then again we will translate the object back. To the original position. Okay, so these three steps are involved in the general three-dimensional rotation. So first we will give for translation, then we will perform the rotation, then again we will translate the object back to the original position. So p dash equal to t inverse rx theta into t into p. So these are the combined three-dimensional rotation. R theta equal to t inverse rx theta into t. So inverse of rotation matrix is r inverse theta equal to r minus theta, cos minus theta equal to cos theta, sin minus theta equal to minus sin theta. So rz minus 1 means rz inverse theta equal to rz minus theta equal to cos minus theta minus sin theta 0 0, sin minus theta cos minus theta 0 0. So then 0 0 1 0 0 0 0 1. So this will be cos theta sin theta 0 0 minus sin theta cos theta 0 0 0 0 1 0 0 0 0 1. So in nutshell we consider orthogonal matrix R inverse equal to R transpose. Then comes concentration of transformation. Concentrating means a fine functions by multiplying together. So you can say of the basic transformation. Define an arbitrary transformation directly. Three successive transformations are there, A, B, C. So we are combining the different transformations in a single transformation, that is called concentration. Then society properties of the matrix concentration. Suppose M1 into M2 into M3 equal to M1 into M2 into M3, M1 M2 M3. So transformation is not commutative. So order of transformation may affect transformation position also. If you are multiplying the changing the order of the multiplication of the matrices, then the transformation position will also change. Suppose if you are checking one direction, then you can see the two diagrams. So in first diagram you can see if you are checking the different two matrices, the position is different. If you are changing the this matrix position, then final position is also changing. So what is composite transformation? So instead of carrying out individual transformation, we are carrying out one single transformation, that is called composite transformation. So if you are translating the object two times, so in spite of carrying out two times individually, we are carrying the single times by using the formulas. So composite transformation is a sequence of transformations, calculating the composite transformation matrix rather than applying individual transformations. So P dash equal to, suppose we are carrying two matrices M2 and M1 are the two transformations carrying out individually. So in spite of carrying out two, we are writing on P dash equal to M into P, means M is a single composite transformation. So composite two dimension transformations in the form of translations. Suppose T1 and T2 are the two translations carried out. So in spite of getting individually translation, we are getting P dash equal to T2 into T1 into P, or T2 into T1 into P. So composite transformation matrix in coordinate form can be given as T into T2x T2y into T1x into T1y equal to T into T1x plus T2x comma T1y T2 plus y. So in the polar form also you can see, in spite of carrying out two polar transformations, in spite we are getting one single composite transformation in polar form. So P is equal to R into theta 1 plus theta 2 into P. So two dimensional scaling is also we can do. In spite of carrying out S1 and S2 transformation, we are getting one formula for P dash equal to S into S1x into S2x, S1y, S2y into P. So in spite of carrying out individually, we can get one single formula for getting transformation. So general two-dimensional pivot point iteration graphics package provide only origin rotation. So we perform a translate, rotate, translation sequence, translate the object to move pivot point position to origin, rotate the object, then again we translate the object back to the original position. So composite matrix with coordinates form is t x r y r into r theta minus t into minus x r by minus r x bar r by theta. So example of pivot point rotation. You can see first diagram original position of object and pivot point. So the translation of the object so that pivot point is at the origin. So we translating the pivot point to the origin point. And rotation about origin we are doing. Then again we are translating the object so that pivot point is returned to position. So these are the steps involved in the rotation. Complete translation also. You can see translation, then rotation, then translation. So first you are changing the point to the origin, translating it, then rotating what is the origin, again translating back to the original point. So these are the common features and these are the common metrics we are using. So general two-dimensional fixed point scaling. So we first to perform a translate scaling translate sequence. So we translate the object to move fixed point position to origin. Then scale the object with respect to the coordinate origin. Use inverse of translation in step 1 to return the object back to the original position. Then compare matrix in coordinate form. So example of fixed point scaling you can see. First we are changing the original position to the fixed point to the original position, then translating the object so fixed point is at origin. Then we scale the object with respect to origin. Then again we translate the object back to the fixed point. So these are steps involved in that composite transformation also of the scaling also. So you can see this diagram also same thing. First you are changing the fixed point to origin, translating, then again scaling about the origin, then again translating back the origin to the fixed point. So general two-dimensional scaling directions are there. Perform a rotate scaling, rotate sequence, composite matrix in coordinate form. So this R inverse theta into S1 S2 into R theta. So the combined matrix becomes like this. General scaling direction you can see. So R inverse theta into S1 S2 into R theta equal to like this matrix you can see. So here I am showing the general scaling directions. So 102 parallelogram. So general rotation of Q about the X Z axis, then rotation of Q about the Y axis. So you can see this question. If you rotate the Q about the X axis, what you will get? So you can solve this question also. So in the diagram, it is showing rotation of Q about the Z axis, then Y axis, then what will you about the X axis. 360 rotations about the 3 axis. So R equal to Rx, Ry, Rz. So combined matrix will be coming like this. Then instance transformations. Instance and objects prototype. Occurrence of that object in the scene. Means there is an object and you are this transforming the suddenly. So what is the desired size, orientation, or location? So this is the instance transformation. The instance transformation is M equal to TRS. Okay, so this is a combined transfer matrix for instance transformation. So we are using this matrix. So what we have learned in this lecture, so 3D transformation is the same as the 2D transformation, but we are considering the Z coordinate also, and we are getting the 4x4 matrix here, 4x4 matrix, 4 element in column and rows also. So 3D transformation is the process of manipulating the view of a 3D object with respect to its original position by modifying its physical attributes through various methods of transformation like translation, scaling, rotation, shear, reflection. So all the these transformations are same as 2D, only the inclusion of this Z coordinate and fourth element in row and columns. And we also discussed in lecture about the composite transformation, then instance transformation. How can we convert the number of transformations into single one by using composite methods. So we have discussed also. So transformation matrix is a basic tool for transformation. A matrix which n into m dimension is multiplied with the coordinate of the objects. Yeah. Okay. So these things we have discussed. Okay. Thank you for your patient listening. Thank you.